Hello, everyone. I would like to welcome you to this session of RoboLaunch. We are delighted to have Professor Simon Lucey joining us today. Professor Simon Lucey is the director of the Australian Institute of Machine Learning and a professor in the School of Computer Science at the University of Adelaide. Prior to this, he was an associate research professor at Carnegie Mellon University in the Robotics Institute in Pittsburgh, where he spent over 10 years as an academic. He was also a principal research scientist at the autonomous vehicle company Argo AI from 2017 to 2022. He has received various career awards, including an Australian Research Council Future Fellowship in the years 2009 and 2013. Simon's research interests span computer vision, machine learning, and robotics. He enjoys drawing inspiration from AI researchers of the past to attempt to unlock computational and mathematical models that underline the processes of visual perception. But the topics of today's sessions are neural priors for open world robotics. So without further ado, I will hand the virtual microphone to our speaker, Professor Simon. Professor, the floor is yours.
Thank you so much for that kind introduction, and thank you so much for the invitation to come join you guys. As I said, unfortunately I'm doing it via bits rather than atoms. I'd love to be there in person and hanging out with all the scholars and all the folks in RI, but hopefully this is second best. And so yeah, so thank you so much for the opportunity. So I guess I might, and hopefully that's coming through. Everyone can see everything. Everything's looking good, and people can hear. So I guess when it comes to robotics at the moment, so much of what we do leans upon deep learning and neural networks, right? And so many of you guys have been working on various projects of different aspects. You've been doing stuff with real-world drones or articulated robots, or you might be doing stuff with vision systems or planning systems, but so much of what we're doing at the moment actually connects to sort of deep learning, and it's really, really amazing to behold what's been happening to the robotics community in that regard. But as we know, and you guys probably cover a lot of this already, is that these neural networks are sort of these abstract things. We love to visualize them. We love to kind of think about them as these sort of graphs that take some sort of arbitrary input X and gives me an output Y. And that is filled with these parameters, these numbers, these magical numbers that seemingly can kind of put things together and create semantic meaning, be able to make decisions. And but a lot of it's still, there's a lot of like black box understanding, right? We have all these rules and other things that we're doing. But one thing I've been really fascinated by is oftentimes we think about neural networks as just sort of a distillation or a reflection of the data that we're training upon. But one thing that's becoming more and more apparent is that there is actual power in the neural network architecture itself, separate to the data. How you, perhaps like the deepness of the architecture, how you initialize the network, how you train the network, all those things actually have knowledge in there too. And one good way to kind of describe that is as a prior. And so oftentimes people refer to this knowledge that is separate to data, that is sort of baked into the neural network itself as a neural prior. And one thing I've been really fascinated with over the last probably year or two is how we can leverage these neural priors for solving all sorts of really interesting problems in robotics. And sort of that's what today's talk is going to be about. And so like neural networks can do all sorts of amazing things, right? We've given that you have a lot of data. I can take some sort of input X and get a Y out, whether it's an image and label it to a cat, or and we call this deep learning or artificial neural networks, or we perhaps like to go the other way. So generative AI, right? We can kind of perhaps provide some text, put it into GPT-4, and I can create images and all sorts of unbelievable scenarios coming out. The other trend that's been happening, and something that the robotics community is really sort of jumping onto, is the amazing progress we've been seeing with large language models over the last couple of years. And I like to, I'm sure you guys have seen a couple of talks on this, but I just like to kind of flag this, especially for sort of junior researchers coming through, and just to behold the amazing progress that we're seeing. So if you were sort of, I spoke about the neural network and the number of numbers in there, we sometimes refer to those as parameters. If you were looking at a large language model, one of the leading ones back in 2018, you're looking at around about like 100 million parameters, right? So that was pretty big. And looking at GPT-3, which was sort of like the beginning model for ChatGPT, in a matter of around about 2 years, it sort of jumped up to 175 billion parameters. And for whatever reason, we love to use the parameter count as the measure of the sophistication of the model. But the thing that sort of blows my mind is just fast forward one extra year, and you've got sort of GPT-4, which is at around about 1 trillion, or actually like around about 1.7, 1.8 trillion parameters in the models. And so if you're looking at this sort of this gigantic increase in, this is not a straight line, this is a logarithmic line, right? This y-axis is a logarithmic scale. Just an incredible increase in parameter count and sophistication of these models. It is such a huge opportunity for robotics at the moment. And one thing to kind of think about too, and obviously, hopefully you guys have been covering some of this in your research and other things, a lot of this can be traced back to the very famous 2017 paper, Attention is All You Need. So probably one of the most highest cited papers in AI at the moment. I was just finishing an AI lecture I was giving yesterday for a class I'm teaching here at University of Adelaide, and we're sort of talking about the different epochs of deep learning. And you very much had sort of the AlexNet epoch in 2012, but sort of you see a lot of what's happening now in AI and robotics, and it's very much sort of reverberating from this 2017 moment of attention's all you need. So hopefully you guys are across this and you are very much using it in your day-to-day research. But what these foundation models can do too is sort of amazing from a robotics perspective, right? So you can kind of like take an image, like, and this is just from the OpenAI website. You can take like an image of like some strange guy attached to a back of a taxi, something probably you guys are used to walking around the streets of Pittsburgh. What is unusual about this image? And GPT-4 can give you some amazing text back, right? It can kind of, the unusual thing about this image is that a man is ironing clothes on an ironing board attached to the roof of a moving taxi. And this is sort of really amazing because prior to this, especially in the computer vision world, which I sort of exist in, we could do things like perhaps detecting the objects, right? You could detect that there's a person there, or detect a car, or perhaps segment the road, but nothing sort of higher level in terms of what's strange about this, what's interesting about this. And what I see as a real opportunity for people in robotics to kind of lean on is it's really a way, these large language models are really a way to project common sense into a robot. And you're seeing a lot of this at the moment. Say, if you ask a robot, go get me a spoon, the robot might not have any idea where a spoon should be located, but say these large language models, you could interrogate it, well, where would be a good place to find a spoon? And well, spoons are found in kitchens. And you can kind of, and that's sort of common sense stuff that you can project back to robots. And so you're seeing a lot of really powerful ideas now emanating in the robotics community about sort of how these big models can be used for common sense and other things, but they rely on huge amounts of data. And we're kind of showing about sort of the parameter count, but we haven't really spoken too much about the data that's involved. The other thing that's interesting too with large language models is that the ideas are transcending language now. So we spoke about sort of like vision and language there, but probably one of the most popular representations of computer vision at the moment is an autoencoder that's used by Meta. It's called Dino. So it's just trained on huge amounts of imagery data, but using largely the same techniques that you're using for language. So again, transformer networks, something called a VIT, a vision and transformer. And you can get all sorts of like amazing reliable segmentations sort of, and again, what's really powerful with these models is previously with a lot of these models, you'd be able to get it working well for one type of data set, but as soon as you're in a new domain or new area, and which is something you face a lot in robotics, the models tend to fail. But because Dino has been trained on so much data, and we're referring to them as sort of foundation models now, they tend to generalize really well, which is, again, a real boon for roboticists. So something very, very useful to use. You guys have probably already seen this also from, I think this one runner-up best paper at ICCB that just went by, Sam, Segment Anything. Again, using similar techniques. But what I love about this is we're all used to sort of GPT and sort of like interacting with it and doing prompts and other things like that. But what's really cool with Segment Anything is it reimagines the idea of what a prompt is. A prompt is perhaps a mouse click or a bounding box, not necessarily text. And so this is another big boon in robotics at the moment, sort of rethinking how can you take these things that apply well to language and applying them completely different domains. So could it be a prompt, or perhaps even the interaction of a robot with the world? And so you're seeing a lot of these world models come out. So especially in the autonomous vehicle sector, things like Gaia 1, and these world models that are coming out. Very, very interesting directions that are sort of emanating. You guys probably heard from my bio that I worked quite a lot in the autonomous car sector for a while. So I worked with Argo AI for a while. That was a really, really fun experience. And you can kind of see like what's on these vehicles. They have like drones, they have ring cameras that are sitting on top. And what's really interesting, right, is that you're playing with sort of data sets there that are really rich, and you tend to kind of get this huge amount of sensory data that's coming in. You have LiDAR, you have radar, you have odometry, you're getting vision. And what you're doing most of the time on the vehicle is you are using neural networks. You're using neural networks all the time. The neural networks there are doing things like doing 3D object detection, right? So you might be doing things like point pillars on the LiDAR. You might be doing mask former or mask RCNN to go and detect and segment. And what you're doing then is that you're doing geometric reasoning, working out where the objects are and working out perhaps the velocity, and then planning and acting and working out what to do. And much like what's been happening in language, these car companies ingest huge amounts of data. And their big play, right, is to be able to generate up more and more powerful neural networks as you collect more and more data, so that the performance gets better and the algorithms get better. And for 80% of when you're driving, that paradigm works really, really well. But and the other thing that this leans upon too is back in the day when we were first doing a lot of this stuff for the autonomous car companies, you had to hire a lot of human labelers to go and kind of draw boxes on vehicles and bounding boxes and sort of say what's going on. But another big boon that's happened out of large language models like GPT-4 and other things is this idea around self-supervision. And so self-supervision is a big trend that is permeating all through deep learning and robotics and AI. And you guys hopefully know what self-supervision is, but typically when you're training a network, just say I've got an autonomous car and I want to have a network that segments people and the ground and vehicles in an image. You used to have to go and pay people to label thousands and thousands of these images. But now what people do is that they're inspired by, and then you have to train up on all these images. And so there's a huge cost associated with perhaps getting enough images to train the networks. So oftentimes, like at Argo, when I was there, the thing wasn't actually how much data you could collect, it was how much data you could label. But there's been so much progress in this in the last even just sort of year and two. It's amazing what you can do just through self-supervision. And so for those of you, you guys should hopefully know what self-supervision is. But essentially, it sort of flips the idea on its head. I don't have these labels. I instead basically get what we call an autoencoder, right? It could be a transformer network, it could be a CNN, and you're basically asking the network to reconstruct the data set that you've been training upon. So instead of trying to map from the input to the output, you're trying to map from the input back to the input. So it's almost a proxy. And a simple thing that you do is just basically this masking. And it's become very, very, especially with transformer networks, with sort of these VIT models and these other transformer networks that are used in language. They essentially do masking to sort of force the network to do something. Because without the masking, right, the network can just be lazy and just sort of maybe do an identity, just sort of say, all right, I'm not going to do anything. I perfectly reconstruct the image. But by masking the image heavily, you can force the network to discover things. But what's really interesting too, depending upon the type of signal, so like images, for instance, need to perhaps be masked at 75, 80% for the networks to actually give you anything meaningful. Whereas say in language and other signals, you can mask at much, much lower levels. And so there's a whole area emerging at the moment in multimodal learning, thinking about what type of masking strategy should you be using depending upon the signal, because it's in some ways almost a proxy for the complexity of the signal. If you've got a very, very redundant signal like in images, you need to mask heavily. But if you've got a not very redundant signal, the masking, you can kind of like back off on that a bit. So that's a whole other field too, which is very, very interesting. But obviously it's not just images. This is how ChatGPT is sort of trained. They essentially just take words out, right? So something walked across the room and you statistically ask, well, you put it back in and you ask the network to predict. So again, really, really powerful. Now, at the end of the day, you still need some labels, right? But this gives you a recipe for scaling up. And so that allows you just to throw huge amounts of data, huge amounts of compute. You're no longer bound anymore by how much labeling you can do. It's really that how much compute and how much data you have access to. So I was listening to a podcast recently, and they were saying that if you are a serious AI company, you can't be considered a serious AI company unless you've got access to at least 20,000 GPUs, right? So like crazy amounts of compute required. Very different to what we experience here in the university sector. So there is sort of this really interesting trend over sort of just scale, right? That we've discovered the secret recipe for AI and super intelligence. And the big thing that we're doing at the moment is just throwing lots of data, lots of compute. And every time we do that, we're getting better and better results. And so something sort of for us to think about. And I oftentimes talk to my students, and I'm not sure if you guys have had the same discussions at CMU, is that it? Should we just all pack it in and perhaps go and just invest in NVIDIA, buy lots and lots of GPUs, get lots and lots of data, and that's it. That's all we need to do to get our research moving along. And you'd probably think that, right? So I've been sort of crowing on about all these innovations that have happened over the last couple of years. And essentially the recipe is this. You get better performance in a deep network if you throw more and more logarithmic amounts of data at it. And a lot of companies are making that play. So they're calling it the scaling play, or they're calling it emergence. The idea that sort of the recipe is basically staying the same, but I get more and more intelligent behavior from something just by scaling it in terms of the size of the network and also the amount of data that I feed it. But there's an issue, right? So, and we found this out even in the autonomous car sector. There's an issue with that. And I think the issue is best summed up by this great tweet that was put out by Andrej Karpathy last year. And I really like it. So I'm just going to talk about the tweet quickly. So Andrej had this sort of tweet where he said, real world data distribution is N01, but a good data set is U-22, right? And you guys are at CMU, so you guys are up with the latest in statistics and other things, but it seems like a cryptic tweet, right? But what Andrej was sort of saying, and I really, really liked, is he's pointing to one of the fundamental issues that we're facing in AI, and especially in robotics. And I think one way to sort of decode his tweet is to take in this image, right? And it's an image that it sort of makes me hold my breath when I see it. It's a small child crossing the road, and it's a horrible image, right? Unfortunately, this child was fine, and you could probably be driving around the streets of Pittsburgh for a couple of years and never see this image, right? It's a very, very rare image. And so one way to kind of decode that is that in terms of sort of an N01, N01 actually refers to a normal, a Gaussian distribution. And so this child instance is very, very rare, never comes along, very, very rare to see. Whereas if I'm driving along the streets of Pittsburgh, I can't go 100 yards unless I hit a stop sign, right? Not literally, hopefully to see the stop sign. I'd avoid hitting stop signs. It's not what they're for. But one thing, right, is AIs need data. Large language models, transformer networks need data. And so the real world is not the ideal data set to train these transformer networks up on, because what I want is I want all instances to be equally likely. And that's where that U-2 part of the tweet comes in. What Andre was talking about is that there's this complete mismatch between the type of data, the distribution of the data that I want to train upon, and the distribution of the real world. And for many robotics problems, it's those those really, really rare instances that are the instances that we really care about and are the problematic instances. And in many ways, it doesn't matter how much data I collect. I could have a vehicle drive around the streets of Pittsburgh for years, perhaps decades, and I will never collect enough data of the rare, rare instances that I need, right? And so, and you're seeing examples of the limits of transformer networks too. There was a, and I'm going to borrow this. This is not my work. This is some work that was at the University of Washington, but it was from a great keynote I saw at CVPR this year. So I just thought of including it for today's talk. It's an example of sort of the limits of GPT-4 when it comes to simple tasks like multiplication. So you guys might have played with GPT-4, but if you actually hop into GPT-4 and I say, hey, multiply 999 by 867, GPT-4 will give you an answer that looks kind of right? 824,133, but it's actually wrong. It actually gives you the incorrect answer. And so it turns out that GPT-4 at the moment achieves only 59% accuracy on 3-digit by 3-digit multiplication, 4% accuracy on 4-digit by 4-digit, and 0% accuracy on 5-digit by 5-digit multiplication. And so this is not a paper of mine. This is actually a paper at the University of Washington. Got a lot of attention. But what it speaks to is, it speaks to sort of how transformer networks learn. So transformer networks tend to look for statistical shortcuts. So if you were to learn the task of multiplication and you had prodigious memory, right? If you could remember everything, how do you learn multiplication? Would you work out the actual steps of multiplication, or would you just treat it as a big lookup table? I'm just going to basically look up this and look up that. And so the issue with treating it as a lookup table is that I can never be exposed to all the instances. And this paper wasn't just about multiplication. They demonstrated a whole class of problems that transformer networks are not good at, especially puzzle solving problems, problems that require sort of intermediary steps over. You notice that you're not seeing transformer networks, say, play chess, for instance. There are a lot of examples like this. And so one thing I'm really encouraging my students to do is to lean in to the amazing opportunities that transformer networks give you, but also really think about what their limits are. And a lot of people just view transformer networks as statistical parrots, like amazing statistical parrots, but they have real limits. And especially when it comes to the amount of data, the type of data that's being fed in and what it can be good at. And so for robotics, that is a real issue, because the ability for us to generalize and apply robots in brand new scenarios and environments is crucial, is really, really important. So how to address this, how to attack this? So at the Institute, for instance, if you've got a robot that's perhaps underwater, sort of exploring a terrain that's never seen before, perhaps on the surface of Mars, where you have no data, you've never been there before. Defense applications, you might have aerial footage of a city or an area that you've taken for decades, but if strife sort of occurs, which is unfortunately happening a lot around the world at the moment, a lot of that data is not useful, right? It's completely different. You've got robots being deployed into sort of high-risk scenarios that it's never seen before, and perhaps even doing things in sort of like a medical AI, detecting rare tumors and rare cancers, things where we have very, very little examples of it. So how to attack these types of problems? And that's one thing that really resonates with me, and one thing that my research group looks at, and also the institute that I direct at the moment. We're very much sort of pushing upon these problems. At the institute that I direct, there are a couple of directions we're exploring. One is causality. So there's this whole area that's emerging at the moment in AI and machine learning around causal reasoning, which I think is very, very interesting. A very famous computer scientist, AI scientist, a guy called Judea Pearl, wrote a lot of influential work in this work, and he really kind of explores this idea of causality and counterfactuals. Counterfactuals are a really important thing for robotics. So if I do this, what would happen here? And so the whole rise of world models at the moment in robotics really connects to some of these ideas. Hopefully you guys know what I mean by causality. Causality is like an example of, say, you oftentimes correlate fires with the fire brigade. But if I were to ban, say, the fire brigade, it's not going to get rid of fires, right? They're correlated, but they're not causal. So the fire brigade doesn't cause fires. They're actually a reaction to fires, right? So there's a difference in that. And so the ability to model how information flows and how it's connected is a really, really powerful way to get around this tail issue, to be able to kind of decouple things. Another obvious one is simulation, right? So the big companies around the world, especially companies like NVIDIA, are investing very, very heavily on simulation. And the main reason is for the child example I gave. When you have a rare instance, you can't have you can't actually entertain some of those instances in the real world. So you need to simulate. But the problem is that neural networks are like errant children. Unless the simulation is perfect, and we sometimes refer to this as a simulation gap, unless the simulation gap is very, very small, the neural network will oftentimes learn the simulator and not the real world. So again, during my time at Argo, we would play with simulators, but you still needed a fair amount of real world data just to even evaluate the model. And so there are limits to simulation. Vision and language. So this is a really, really interesting, and in many ways it should be expanded. I would call it multimodal learning. So instead of just learning in one domain, so have a system for learning just in vision or a language or audio or haptics, just doing them all separately, actually learning them all at once. And there's a real opportunity to do that at the moment with transformer networks. Transformer networks are really powerful because they're essentially universal learning mechanisms. You can apply a state-of-the-art nearly in every domain of AI, vision, language, speech, robotics. They are all drawing upon transformer networks. And so it allows you to have a unified framework to learn. So vision and language is probably the best example of this. But what's really powerful, right, is something that's rare in vision may not be that rare in language, and vice versa. So you can make up for shortcomings in one modality by leaning into another. And there's a lot of sort of evidence to say that we humans actually really lean on multimodal learning a lot. And so that's one area that I'm very, very bullish on too. I think multimodal learning is a very, very interesting direction. And the last one is sort of neural priors, which I was sort of like flagging as sort of an interesting one that we've been doing a lot of work on, which is sort of more leaning into how you can play with the architectures, the initialization, the optimization of a neural network outside of the data it's been trained upon, and potentially get some very, very good results that circumvent some of the issues of just being totally beholden to the data set that you're trained upon. So I'm gonna, for the latter part of this talk, I'm gonna talk about some of the work we've been doing with neural priors. Probably the best example of neural priors are neural radiance fields. And I would be guessing in robotics, I'm seeing a lot of work coming out at the moment using NERF. NERF stands for neural radiance fields. And so it was a paper that came out by out of Berkeley in 2020. The idea is pretty simple. And I've got a reminder here of what it's trying to do. What you're trying to do is you perhaps have some images and you're wanting to reconstruct the radiance field of a scene. And a radiance field is typically modeled like a 5D field. You perhaps have the 3D position plus the viewing angles. That makes the 5 dimensions. And what you're trying to do is just sort of basically, if I take a set number of images, perhaps I've got a scene where I've got 10, 12 images of a scene. what you can do is you can try to model, just from those discrete number of images, you can actually try to model the continuous radiance field for the entire scene using a neural network. So almost the opposite problem to what we're doing with transformer networks. Transformer networks needs millions, if not billions of examples. NeRF can give you amazing results with perhaps 10, 12 images. That's it. And so that makes it very appealing, especially for robotics companies and universities where you've got limited compute and data budget. You can actually get some really, really amazing results. One thing I was involved in, so I'm not going to give a big tutorial on NeRF. It's been around for ages. One thing that I was involved in 2021 was some work that tried to combine ideas from SLAM and NeRF together. So we did some combined work with Antonio Tarabla at MIT and one of my previous PhD students, Chenchuan Lin, who's now at NVIDIA and doing a lot of kind of really cool work there. What we explored was this idea of trying to solve for the neural network that reconstructed these radiance fields and the poses at the same time. So it's something called BARF, so bundle adjusted radiance fields. And the idea was pretty simple. It leaned upon an idea that's very popular in language models at the moment in transformer networks, positional encoding. And it turns out positional encoding is really important for radiance fields. So, and all positional encoding is, it basically takes an arbitrary position. So I can have a position in 3D. And what it tries to do is it encodes it using different sinusoids of different frequencies. And so, and it's really crucial to make NeRF work. But what we found is when you're solving for pose with NeRF, it can be catastrophic because you can actually get stuck in local minima. It doesn't estimate pose well. So we drew inspiration from some classical ideas in computer vision. So essentially this idea of coarse define, and you might have covered this in computer vision class, but all we did was when we're solving for pose within a radiance field, we started with low frequencies in the positional encoding and slowly over time through a scheduler added higher and higher frequencies to the positional encoding. And so, and basically that allowed you to get really nice performance. And so people started using that a lot, and it's been quite heavily cited in the last probably 2 years. Last year, we came out with an extension to this, something called GAF, which is called Gaussian Activated Radiance Fields. And what this leans into is sort of some of the narrative that I'm talking about is we actually rethought, again, nothing to do with training on data, just about the architecture. And one thing we were exploring a lot is activations. And activations is probably something that you guys don't think a lot about with deep networks. You probably use ReLU or GLU, and then that's it, right? You don't think about the activations. But in NeRF and neural radiance fields, activations are crucial. And so what we advocated for is instead of using ReLU or even sinusoids, we put forward a whole theoretical premise over the use of Gaussian activations. And there's a whole rationale for why, which is probably a whole other talk. But probably the simplest thing is it sort of connects to this idea of if you've done any signal processing, Shannon showed that sync functions are, for a band-limited signal, the optimal activation that you can use. And so a very good approximation of sync functions are Gaussians. And so we sort of put forward this theoretical framework for that. But what's really nice are the results. So we showed in our paper that, say, if you're trying to, this is a toy example, if you're trying to reconstruct an image as a neural network, and you also want to do the alignment at the same time, you can kind of compare these things together. And you've got BARF and you've got GARF, which are probably the two leading techniques. There's also this technique called Siren. And you can kind of see here these boxes. These boxes are trying to do alignment and reconstruction at the same time. Now, BARF gives okay results, but it's complicated. You have to have a scheduler, you have to do coarse define. GARF is really powerful. GARF doesn't need any scheduler. It works out of the box and it gives you very, very nice results. And you can kind of visualize this here. We've got an example of sort of if you were trying to model a NeRF using sort of just a naive method, just try and solve for pose. We can kind of see here on the left, the poses are oftentimes wrong or incorrect, but with GARF, you get almost perfect pose out. And so what's really interesting is it's opened up a direction for us where we can start exploring ideas around using radiance field and SLAM together. So you're solving for pose and a radiance field of the world all at once. Now, oftentimes, and can get nice things with this too. I can reconstruct brand new images from new vantage points, but I also get sort of depth, right? I get depth for free. I don't need to have LiDAR. I can actually get a nice depth reconstruction as well. Some other examples, flowers. And we've also found too that one of the rationales for this that's nice is that if you're using a conventional SLAM system, SLAM is very, very dependent upon how textured the scene is. And what I mean by textured is that if you have big changes in the pixel intensities, so if you enter an area that's not very textured, so like in an area like this, where you've got sort of like a plain white wall with stairs, regular SLAM can fail quite dramatically. Whereas if you apply things like GAF to this, you can actually get really nice results in low textured areas. My group's also been doing a lot of stuff in deformable NERF. So NERF has been sort of like really aimed initially at static scenes, being able to recover new vantage points from static scenes. But increasingly, people want to kind of do dynamic scenes, and robots are no different, right? We want to kind of like simulate the real world. And so we've got some new work that just came out at CVPR where we've been able to extend upon a lot of recent work in dynamic NERF. And you can kind of see some visual examples here of sort of the improvement in the system that we have. This was some work that was done by, again, a CMU student of mine that just graduated, Chaoyang Wang. He's at SNAP now. And again, some really nice work. And we're connecting some classical ideas with optical flow, with dynamic NERF. And again, this is a whole area that's very, very active at the moment. The other thing that I've been really excited by with neural priors is the application of ideas like NERF and other things to areas other than images. So one thing we've been looking at in robotics a lot is LiDAR. LiDAR is a great sensor that's used in a lot of robotics problems. And one problem that we're really interested in LiDAR for autonomous vehicles is scene flow. But one thing we're noticing is that there are a lot of data sets that are out there. So Kitty is probably one of the best known data sets for autonomous vehicles. There's a scene flow benchmark. And there's been a lot of kind of great papers that have come out in the last couple of years. But there was a paper that I was involved in with one of my Ph.D. students, Nate Chodosh, and Deva Ramanan, who's here at CMU. We were kind of showing that actually a lot of these leading techniques actually on newer benchmarks like Argoverse, actually the results go up. The error doesn't go down, it goes up. And this is sort of showing that some of the classical data sets that people are working with are sort of saturated. And also it speaks to, again, this mismatch in data. So I could train on Kitty, but then I get very, very poor performance if I slightly change the LiDAR sensor or deploy it on a different vehicle, which is a real problem if I'm working in robotics, right? I want an algorithm that sort of works well. If I switch out my LiDAR for a new LiDAR or I set up the device differently, I don't want to have to go and collect thousands of hours of new data to be able to use the sensor properly. So one thing we explored was this idea of trying to solve scene flow in a different way. And so to remind you guys of what scene flow is, I perhaps have some 3D point clouds. So I've got PT, I've got N1 points in frame T, and I've got N2 points in frame T+1. And all scene flow is trying to do, it's trying to work out how to kind of flow or move the blue points to the green points. You can kind of see them here, such that I minimize some sort of error. And for perception in a robot, that's important, right? Because I want to know what the movers and the non-movers are. So if I'm a vehicle I'm driving through, I'm a robot going through a scene, I want to avoid things that are moving. And so scene flow is a great way of determining what's moving and not moving in a scene. And what's powerful with it, it's open world. I don't need to know whether it's a person, a car, a bike. If it's moving, I avoid it. If it's not moving, I get out of the way. But it's actually really, really hard to do that well. So, and you can talk about the flow as being F, the vector that kind of maps between the two. And typically how one way to solve this, and this is a paper that we had back a couple of years ago, was to minimize the chamfer distance between these 2 point clouds. And if you don't know what chamfer distance is, it's essentially, it's very similar to ICP. It's like a metric from ICP. It's essentially measuring the Euclidean distance between 1 point cloud and another point cloud, given that you're making an assumption about the correspondences. So you find the closest points between each point cloud, and all you do is measure the least squares error between them. That's all chamfer distance is. And so we put forward this idea of, well, SceneFlow, a simple way that doesn't need a neural network is just to minimize the chamfer distance. And then we had this regularizer term that we added at the end. And at the time, we were really struggling to work out what the regularizer should be. And the reason we need a regularizer is without the regularizer, just minimizing chamfer distance, it's a bit like optical flow. You get all sorts of spurious flow estimates. But by regularizing, it makes sure the flow estimates are all working together. So if I've got a flow estimate in one position, I want the flow estimate next to it to kind of move in that same direction. So how do I choose that regularizer? And so it turns out that a great regularizer is a neural network. And this is an example of a neural prior. So I'm not taking a neural network that's been trained on hours and hours of data or millions and millions of examples. I'm taking a network that hasn't been trained up on anything at all, but I've chosen the architecture such that it naturally smooths out and regularizes the solution. So the idea here is instead of solving for the flow, I solve for the neural network that represents the flow. And the architecture of the neural network implicitly regularizes the problem. So it's sort of an elegant idea. And it's something we call neural scene flow. And so is that NeurIPS in 2021. And it turns out a lot of autonomous vehicle companies are using this now because it just works. It doesn't have any mismatch. It works with different LiDARs, different setups. The idea then is that you're just, instead of doing this big complicated regularizer, you're solving for this neural network. And so what's nice with it is that you can potentially densify LiDAR, for instance. I've got sparse LiDAR on one scene. So this is an example of sort of just LiDAR from a scene. And I can amalgamate LiDAR sweeps over time using neural scene flow and do things like this, make them dramatically denser, just using, and again, there's no training data here. It's actually using the architecture of the neural network to regularize the problem. Oftentimes people say, well, that's not very practical, right? Because you are having to, one of the problems with it, right, is that I'm training the neural network at runtime. Conventionally, when you're using neural networks, we're used to them being frozen. They're trained for days or weeks offline. And then when we deploy them, we want them to be fast, right? So they're frozen. So, and that was correct, right? So if you looked at sort of when we first came out with neural scene flow prior, this is on the x-axis here, we have time in log scale. And on the y-axis, we have error. And you can see that when we first came out with the paper, we had tremendous error, right? Compared to some of the leading neural network-driven methods, data-driven methods. But these neural network methods were way faster than our method. So it wasn't really practical for robotics. But just this year, we've come out with an extension for, we've called it fast neural scene flow. And what it enables you to do is it basically draws upon some classic ideas in graphics and computer vision, especially around distance transforms. So the big cost of this was actually doing the chamfer distance. So there's this idea of actually pre-computing a lot of the distances using something called a distance transform. And by doing that, we've actually got a method now that is actually faster than a frozen neural network, leading frozen neural networks, but trains a neural network at runtime. It's a test time optimization, and it's just as fast with no data. And again, just leaning on this idea of a neural prior. And so this was a paper at ICCV just from 2 weeks ago, I think. And one of my students, Sushin Lee, who did her master's at CMU, but is now doing a PhD with me at Adelaide. We've extended this too. We've extended work. One problem with neural scene flow prior is that it sometimes tries to blur the edges between objects. So if I know I've got a rigid object like a vehicle, I don't want scene flow on the edges of the vehicle to be blurred with the background. So we've also included some ideas of isometry and rigidity in there. So we've got a new technique that's able to kind of take advantage of this. And so it does sort of some clustering and some other things that basically ensures that if you're inside a cluster, you're ensuring the points move as sort of a rigid body, but it still allows you to have the flexibility of the neural scene flow. And so this paper was just accepted to 3DV. That's coming up. Actually, it's 3DV 2024. It should be early next year. But we've dramatically improved the accuracy of this. So we had neural scene flow prior. Waymo came out with an extension to our approach called neural scene flow prior ++, and we've improved that again in this latest paper. Again, if you're working in this space, I encourage you to check it out. And you can also kind of do cool things with this work as well. Instead of just doing scene flow over 2 frames, you can actually do long-term tracking. And so this is a big field that's emerging more and more in computer vision. So instead of just tracking doing optical flow or scene flow between 2 frames, actually having points move over large areas. And you can kind of see this here. And so what's really powerful there is that you can segment things out. And one direction that I'm actively working on at the moment is this idea of open world perception. So being able to kind of coming back to that idea that at the moment, when we're doing stuff in autonomous vehicles, we're trying to do closed world perception. We're looking for people, bikes, vehicles, and we've got a list of all the things we're looking for. But at the end of the day, what we really care about, what's moving and not moving. That's the main thing we care about. And so a really great way of determining that is solving scene flow, and solving scene flow in a way that you don't have to have billions and billions of examples of each class to be able to do it. And so this is, Waymo had a paper that came out last year on this. And so we've got a paper under preparation where we're using neural scene flow at the moment to sort of, in a generic way, better solve this open world perception problem. The final thing is some of the work with physics-informed or sort of neural priors also can be applied to physics, which is really, really interesting. So we've been working with some physicists in some other areas here in Adelaide. And so one problem, right, is you don't need to be solving a radiance field or perhaps scene flow. You could perhaps be solving something like the wave equation or Navier-Stokes or any type of sort of like physical form. And the problem sometimes is that I've only got a sparse set of observations, but I perhaps know the physics. So I could actually sample lots of points and enforce the physics here. And so that's something called a physics-informed neural network. And it's got lots and lots of attention at the moment. But it is essentially a nerf. But they're enforcing physics in observations where they don't have any real-world observations. They're just enforcing the physics on top. And so we've got some recent work where we've been able to apply some of these ideas to things like Lorenz attractors. We've got Navier-Stokes. We've got other problems where we can apply these techniques and actually get really good reconstructions, much better than a lot of the techniques that physicists are using. And so that's a whole new direction that we're trying to develop up. And that's we've got some really exciting projects that are sort of evolving in that direction. And we've got a couple of papers in this direction too. So just in conclusion, there is a really open problem on how architecture, optimization, and initialization in neural networks relate to priors, right? So one thing I really sort of want to get people thinking about is neural networks are not just a reflection of data. The choices you make with respect to the optimization, the initialization, and the architecture also dictate some knowledge about the problem. And so really being thoughtful about that and how you leverage that can lead to great results. In fact, sometimes you don't need any data at all if you do that properly. And so this whole area of NERF, and sometimes people refer to this as a coordinate network. I think another thing that's really exciting is that at the moment we're using deep learning a lot, but we don't really have a lot of good fundamental understanding about why it works and what's going on. And one thing I love about the work we're doing in this space is it's really giving us greater insights into the broader field of deep learning and robotics. So yeah, hopefully that was interesting. Thank you so much for your attention, and I'm very, very happy to answer any questions.
Thank you very much, Professor. That was very insightful talk. Well, for me, the neural priors are like very new topics to me, and I'm quite amazed by the advancements in this field. Well, I'm also still under the impression of the advancements in computer vision, the pace of the progress in those fields are amazing. So thank you very much for this. We have a couple of questions from chat, so maybe I will start asking those. So the first one is, safety is one of the most critical aspects of robotics. If neural networks are basically black boxes nowadays, how should we go about when deploying such systems in the real world? How far is the research when it comes to providing safety guarantees in such AI systems?
That's a really, really good question. And sort of goes to the heart of some of the research that we're trying to do, right? So one way that we think about neural networks, right, is that they're sort of these data-driven systems. And so it's very, very difficult because we don't really have any good understanding about how it's making decisions. Like I had the example with GPT-4 over multiplication. It's really hard to evaluate, is GPT-4 really learning multiplication, or is it just memorizing multiplication? That's very, 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 very difficult for us to ascertain. And so it's a very, very similar problem in robotics applications. How do I know that just because it works well in my test set, will it always work well? So one direction that this is why I think neural priors is a really, really interesting direction, because you can get really good results using very little data. And so techniques that at least decouple your performance from data, I think is a really, really powerful way to do that. The other way is sort of what the big companies are doing, right? So the big companies are making models so big, so large, that they tend to sort of generalize well. So and that's what's been really amazing, I think, in the last perhaps year, like looking at things like Dino. If you're doing anything in robotics, I'd really recommend you guys checking out something called Gaia 1, which is been put out by Ricoletti-san. They're talking about these things called world models. So there's definitely things that can be done in that way, but like one direction I really like is trying to decouple yourself from data as much as possible. But it is a real open problem over how can we guarantee that for safety situations that we know that these models are going to work as well as we want. Another thing is one way to think about why I think a lot of companies are very interested in investing in NERF is another way to think about NERF. It's a way of doing data-driven simulation. If you think about how simulators were built years ago, they were basically kind of like gaming engines, right? You can basically get a gaming engine and you could kind of make it kind of look like the real world. But when you looked at the simulation, you always kind of look like, oh, well, it's not quite right, or it doesn't look quite right. What's really powerful with generative AI now is that you can generate imagery that looks quite believable, right? And so increasingly people are moving towards these, and NERF allows you to, for instance, Waymo recently nerfed all of San Francisco. And the reason that they did that is you can have your vehicles moving around San Francisco, right? But perhaps you've never gone down that one street or made that slight twist here or movement here. NERF allows you to do that in a really data-driven, realistic way. So I don't think there's going to be one silver bullet. I think, and I sort of spoke to that, I think things like causal reasoning, I think multimodal learning, I think data-driven simulation, and I think techniques that really unlock a better understanding of what's happening in deep learning so that we can have better proofs on sort of guarantees of performance. We need to do all of these things to ensure that we have some confidence of our robots being deployed into high-risk scenarios.
Thank you very much. So I guess we have a silver bullet here for the computer vision.
I don't know if it's a silver bullet, but it's there are a ton of, and that's the exciting thing. I think if you're a student, there's lots of interesting directions to pursue.
Yeah, definitely. So maybe let's take another take on this topic from another perspective. What are the limitations and challenges when it comes to neural priors methods? Because the data is not a limitation anymore. So
exactly. So I think one of the limitations is, one of them, for instance, is with a lot of these techniques of neural priors, they require runtime optimization. So one of the big things is actually most people, when they're using these sort of techniques, they want it to be instant, they want it to be fast. And the original NERF paper, for instance, it took hours. Like if you just wanted to reconstruct a couple of new images, it took hours to do. There's been a lot of great work in speeding that up, but that is a big barrier in terms of sort of doing that. The other big barrier, I think, too, is how to include. In some ways, it's gone too far one way. It doesn't. You can get great results with, say, 12 images or 11 images. But if I've only got 1 or 2 images, I would like to be able to call upon data to help me. So one sort of challenge is, how can I inject machine learning into these frameworks? And there's been some really nice recent work around that. One paper in particular I would flag, again, it came out of Berkeley, Matt Tannick's group. It just came out at ICCV. It's called LERF. So it's embedding, say, clip embeddings, like language embeddings with NERF, which is really, really neat. If you haven't seen it, check it out. You can actually kind of go in and get like this really sort of fantastic 3D reconstruction of a scene. And then you can type in sort of open world text, say, sort of like pot plant or shelf or other things, and it will segment it like a lot of these other things do, but it segments it in a 3D consistent manner. So no matter how you move or where you work over it, and so it makes actually the whole system better. And so I really like that too. I think that's a very, very interesting, a really open challenge. The other one that I think is really exciting that I kind of flagged at the end is, I'm really excited about how you could adapt some of these NERF type techniques to physics. I think that could be a really, really interesting problem. So I think applying things to sort of new areas of science, I think that's a whole area that is still largely unexplored.
yes, thank you. And I also think like this, like it's particularly interesting that this research is like conducted right now, and like the updates are so fast, and we can see the progress like on, right now and on our eyes. So I guess it's, well, I guess also a lot of things will come, but it's still very interesting. Okay, we have another question. You mentioned 2 or 3 research projects that are now being used in industry. In Australia specifically, how is the relationship between industry and academia?
Yeah, it's a great question. So I think you guys are really spoilt in Pittsburgh. Pittsburgh, through hard work and just sort of excellence between industry and academia, you guys take that for granted. So I don't think we're quite as far along as some of the cities in the US, but that's changed quite rapidly in the last couple of years. So I guess there is a real thirst at the moment for robotics and machine learning talent around the world. And so they've identified that, say, places like Adelaide have a lot of that talent here. So say Amazon Research has set up base here in this area. So a lot of my students and even academics, they're working for Amazon at the moment. We have very strong relationships with Apple. We are doing a lot of stuff with a number of other robotics companies, and even companies that are sort of in the area. There are, you guys may not be aware, but companies like, say, Vin AI, for instance, which is a big sort of like tech company in Vietnam. They're looking to have set up relationships with us. So there is sort of a real sort of awareness and emergence of sort of that talent. And I think sort of like if you look around the pockets of excellence around the globe, you will see industry partners connecting up to them. So whether you're in Europe or Asia or Australia or the US, and one of the privileges you guys have at the moment is being at CMU, you see that firsthand because companies try to set up locally to all the top talent to get access to students like you guys so they can kind of feed the innovation engine.
Yeah, we see that. Thank you very much for the answer. Following up on this, because I know you have been like working in CMU for over 10 years. Yes, that's true.
Yeah.
So you are familiar with the US and as well as Australia. and the research experience in both countries. So how can you like speak more or share the like differences or like between research in US and Australia?
No, great questions. I think both are good, right? I mean, I wouldn't really change a thing. I really, I treasure my time that I had in the States. I still treasure it. Like my wife and all my kids are American, so it's sort of like very formative time. I think that there's a lot of exciting things happening here in Australia too, especially in terms of we have similar landmass to the US, but a a much smaller population. So in terms of sort of big robotics problems, I kind of argue to the federal government here that obviously the US is a powerhouse in robotics, but Australia potentially is one of the countries that has the most benefit from robotics because we have such a large landmass and such a small population. And so if you're looking for super challenging problems in which to deploy robots into them, I can't think of anywhere else better than Australia to deploy robots and try them out. But the other thing that's really important too is I don't think either place can do their research or their work in isolation. Like that's why I think it's really important for us to form really strong links between institutions like CMU and Adelaide. I think it's really important for multinationals to have research presence and innovation hubs in both countries. And what I'm really big on too is that swapping and that exchange of ideas. So really keen, I'm very keen to see Harrison over there kind of joining RIS at the moment during that. And it's those formative experiences of being in places of excellence like CMU that's really valuable to Australia, but also CMU gets a lot out of, it's not just Australia, all the talent that's in Asia, Europe, South America. The world's richer when we exchange ideas and share information with one another.
Well, thank you for that. Well, I come up from Poland actually, so I'm also like international here. So I see also that the research is open for international people as well. So.
It's my memory from CMU. CMU just seems like a large extension of the UN, right? It's just sort of people from everywhere. So that's what makes it special and amazing.
Yes, that's true. That's definitely true. Oh, we have here at the Zoom a question from Pablo. Pablo, can you speak up?
Yeah, can you guys hear me? Am I audible?
Yes, we can hear.
Yeah. So I was wondering, well, first of all, thanks for the talk, Dr. Lucey, very interesting topics. And I was wondering, was this path towards making neural networks architectures more generalizable? It seems like a very big part of that is having more intent when designing the architectures, right? Being a bit smarter with how we're processing information, especially with like physics informed. So I was wondering how this generalizability, which contributes to simpler networks, also impacts the implementation value of these networks. Have you noticed a correlation between the two?
Yeah, no, I think that's a really great question, right? I think that, and it's funny, I don't pretend to have all the answers with this, but one thing I do think about, and this is sort of something for a lot of the young people listening on the call about, is that I think rather than being at sort of we've solved all the questions with AI, we're really at the beginning part, right? I kind of liken it a bit to when the telegraph was first invented in the 19th century. People were making millions of dollars by building telegraphs, right? Kind of sending information, doing things. But at the time, no one had any clue about information. They didn't have even the equations of information theory or bits or how far. They were just engineering things to get it to work, right? I feel that we are in a similar age, that we've sort of stumbled across the recipes for doing sort of these amazing intelligent tasks, but we really don't have a good understanding of the fundamental principles that are involved. And if you fast forward like 100 years, you see now we needed people like Claude E. Shannon to come along and sort of like really open up information theory. As a result of that, we don't have better telegraphs. We have a completely new, different innovation system, right? Sort of things that technology that they never ever thought of. That's what I'm really hopeful of with this age of AI. I don't expect sort of, if we get big theoretical insights from AI, for us to have better ChatGPT. That would be a disappointment. I think the insights that we come from here will hopefully put us forward to solve problems that we're not even thinking about, sort of whole domains that we're not thinking about. So I kind of joke, we need a Claudie Shannon, whether it's a boy or girl or whatever, who of intelligence, of AI, and really unlocking some of those fundamental properties. And for me, that's the big challenge of the 21st century. Whoever does that, we're gonna be solving problems that we weren't even thinking of.
Thank you so much.
We have another question from the Zoom. Leo, can you speak up?
Yes. Hello. Can you hear me?
Yeah.
Well, okay. So you mentioned that the state-of-the-art models are becoming more and more data hungry, and the number of parameters is increasing. And so I was wondering, considering that academia usually has less computational resources than industry and less access to data as well, how do you see in the following years the impact of the research being done in academia versus the research being done in industry?
It's a really good question. I think it's one that you probably don't see a lot of your professors talking about, but it's probably one that keeps them up at night. It's a good one, right? I see a couple of things happening. I think one thing you see a lot, right, is industry releasing foundation models or open source models, and then academia and students basically leaning into them, right, using them in interesting ways, extending them, applying them. And so you're already seeing that. I think that trend's going to really extrapolate or accelerate, sorry, not extrapolate. The other thing, a trend I see happening would be around the edge. At the moment, I think we've got this hive mind mentality around AI, like everything has to be on a HPC, everything's back up from the cloud and other things like that. And in robots, we just can't do that, right? If I've got a robot that's trying to lean on ChatGPT or other things like that, and I am, if I've got a communication issue, I'm on the surface of Mars, or I can't do that. So the whole push of shifting things to the edge, and we saw this happen. It's almost like a repeat of what happened with the AlexNet. AlexNet could only run on a big GPU at the time, and people did all this work on how can I quantize, how can I get the bit rates down, and so I think roboticists are going to be doing a lot of work on this. So how to get AI running on the edge. And so I think there's a lot of innovation to be done there, and also sort of in a heterogeneous manner. So kind of like distributing the compute. So I think that's a really, really exciting direction. And then the other thing I think where there's opportunity for academia, right, is that industry it's going to be interesting to see what happens in the next couple of years. But you are getting to a situation that even where industry is going to get a bit cautious about building bigger models, we're going to see bigger models, right? But every time you build, if you get a model that's order of magnitude bigger or order of magnitude more data, it costs you order of magnitude more money to train the model. So you are getting to this thing where they're doing calculus over sort of like, well, how much money are we actually bringing in for this update? Like, how much more is this going to cost, right? And so definitely we've got new chips coming out and other things, but that is going to be a barrier that we're going to have to think about. So I think that's the other thing too, and also kind of giving guarantees. So increasingly, and I hear this in industry sometimes, we don't always have guarantees that perhaps if I throw an order of magnitude more data at it, do I actually get a tangible performance gain? So companies will be looking for guarantees. Okay, if I am going to do that investment, can you guarantee to me that the performance will go up? And so that is a whole thing. And so that's where actually there is a need for better theory, because theory, no one cares about theory, but when you get into this type of stuff, right, that's hundreds of millions of dollars. And you want to have proof and guarantees that that investment's going to lead to a performance gain. So that's a big problem I see.
Okay, thank you very much.
And also, like the fact that some companies still open source those models, it's also like very, very inspiring, because they invest so much money in training those things, and then just open source is just to build community and foster research.
I think it's not. I think it's inspiring and potentially inspiring. I think it's also perhaps a very, very shrewd economic move, right? So if you kind of look at, again, I don't want to be, maybe it's just my age shining through, but say you can think of foundation models as the next iteration of operating systems, right? So one reason that Google put Android out there, right, is Android, they're not doing it to, I mean, it's great, it's open source and other things, but really what it was is a way of getting market share. And I think it'd be the same thing. So if you get developers using a foundation model because it's open and other things, and they become dependent upon it, then the next iteration you got through there, and then you own that whole space. So in some ways, I see that's what's going to be happening with foundation models. Foundation models are going to be the next iteration of operating systems. And so basically, and you've got just what happened with operating systems. You have closed operating systems like what Apple did. And then you've got open operating systems like you see with Android, and different strategies, right? And so I think you're going to see something very similar with foundation models. Different companies will be pushing on the strategies differently.
So, Professor, you think that they want us to like make some kind of a vendor lock-in for their models? Yeah. Okay.
Again, I would not be doing any investments or anything based on what I'm saying, but that's that's one thing that I see. I kind of see that, and it's laudable and fantastic that they're doing it open source, but I think there's a strategy to it too, and it's good to be aware of the strategy. And I would believe that's why they're doing it.
Sure. So let's just move to another bucket of questions. From the technical point of view, we have like a lot of stuff already talked about, but there are also students and here listening to us, and they are like interested in some questions about research opportunities and such. So are there any research opportunities in Australia or University of Adelaide for international students, and especially undergraduate students?
Yes. So we have a slew of opportunities. So we have our scholarship rounds. So we have scholarship rounds very similar to CMU. You go, and I'm very happy to, if you go to our website, the Australian Institute of Machine Learning, you can kind of see details over some of those opportunities. But if you want to directly reach out to me, be very happy to answer them. But we have 2 rounds a year. And you can apply for undergraduate, master's, and PhD level. Most of the students working with me tend to be master's and PhD level, but I do actually teach some. We have this weird thing in Australia called honours, which is sort of a, if you know the British system, it's sort of it's like it's the last year of your undergrad, first year of masters. Harrison can probably explain it to you. It's in between. So we do teach courses there, and in all manner of things. So at the institute that I direct, we've got about 12 professors, and we're touching upon different areas of like reinforcement learning, robotics, computer vision, straight AI, and one thing that we do a lot of too is that we do a lot of collaboration. So for instance, I've got like ex-master students from CMU that are doing PhDs at Adelaide, vice versa. We're increasingly sending students from Adelaide over to CMU. And and we're very interested in international students applying, and there are a number of exciting opportunities. And just like CMU too, what we try to do, especially at the graduate level, is we try to place students in interesting intern opportunities. So a couple of my students just got back from Cupertino at Apple, for instance. So they're examples that they're working on there. And then there's Amazon right next to us. A number of our students, a lot of my postdocs have actually been hired by Amazon. So there's a number of job opportunities. And so, very, very happy to answer more questions.
Yeah, I see there's lots of going on in the University of Adelaide. That's great to hear. And next question is about the PhD. What are some of the differences between entering the PhD in Australia and the US? Is there a hard start as in the US?
Yeah, so that's a really, really good question. So it is slightly different. Basically, largely the end result is the same, but there are some subtle differences. So at CMU, for instance, if you're coming in cold to the PhD system, you have to do sort of like 2 years worth of graduate work. Like obviously, if you've already done your master's at CMU, you typically get exemptions out of that. So it's sort of similar in a sense that we tend to give students exemptions when they come in. So it's typically kind of similar. So if you're coming in, it's typically a 3.5, 4 year period. Similar intensity. So you'd be publishing at sort of like top tier conferences like so ICRA, CVPR, ICLR, NeurIPS, places like that. In terms of there is no hard start. So in the US, everyone sort of comes in at the same point. You can start at different points. But the scholarships are given out twice a year. So, but you can kind of start at different points. But we definitely have like an orientation, and we have a whole program here for the students. So that's basically the process. Just like in the US, the stipend and tuition's all paid for, so you wouldn't have to be paying for anything if you get into the program. And we give you kind of compute and other things. And then we try to, at least in my group, and I know that that's true with a lot of other professors, we try to at least give you at least one internship during the process at a company, because I think that's just very useful during that process. And I like to do it perhaps halfway through the PhD, because it's good to get a paper or two under your belt. I think one thing that we're trying to do, I think it's good coming in from the master's if you've got that sort of graduate coursework base in. But if you're coming in out of undergrad, there are scenarios where you can kind of get in, but that's where we'd encourage you to kind of do a bit more coursework and things. And so I think the CMU PhD is an amazing process. And so you can kind of get through. But I would say one of the advantages of the Australian system is that if you're in a hurry to get your PhD, you could probably get through faster. Not that I always recommend it, but say if you're coming in cold into the CMU system, it might be like 5 years, because you'd have to do 2 years of coursework plus the 3 years PhD. Whereas in Australia, you'd probably get through in about 3.5, 4 years. So you can probably shave a year or two off, but similar. So that's the process. And then for the international students, we have 2 lots of scholarship rounds.
Okay, it's actually very similar to Europe, that in Europe you apply usually after masters, not after bachelor degrees. So yeah. And then maybe the last question, because we are running out of time. What do you look for in students that apply to your research lab? How to create a strong application? Yeah,
great question. So I kind of typically do a couple of things. So I don't necessarily, I think some professors make the mistake of sort of like, they want to see CVPR publications already and other things like that, which is, I think, very, very difficult. And oftentimes you miss a lot of the diamonds in the rough. So I don't normally just go from that. Obviously, if you've got a publication or two, that's great, but that's not a big thing. I think the big thing is if you've got a good grounding. So if you've done some graduate work or some other work like that, you've interned somewhere, if you've got a letter of recommendation. So for instance, if you've gone through this process through RIS or whatever, and you've got a letter from someone, that counts a lot to me. So that really counts. But the big thing is actually what I love doing is I like looking at sort of the fundamental processes that are going on. So if you are kind of applied, you like working in industry, but you've also got a bit of a flair for sort of some of the mathematics and undercurrent for what's going on. I find that's the type of student that I really like working with. But I also really enjoy students who like to build things and make things. So there are a lot of things going on in Adelaide at the moment. So we've got different projects for different people. So if you've got a strong resume, I definitely encourage you to apply, and we've just recruited another professor from the northeast of the US. So we're actually recruiting a lot of extra professors too at the moment. And so there should be some more opportunities coming up.
Thank you very much, Professor. I think we should wrap it up. And so thank you again for your time here, for answering the questions, for your talk, for all of the time together. And for the audience, also thank you very much for joining us today. And see you tomorrow on another RoboLaunch. And take care. Goodbye, everyone.
No problem. Thanks so much, guys. Appreciate it.